Brownie import lottery. In order to deploy this, we're going to need to get an account. We are going to import our helpful scripts from the last project to this one too, so we can get our get accounts, but for the time being, we can actually just use accounts 0 from Brownie. So we'll say accounts 0. Let's just start with def. Then we'll do lottery equals lottery.deploy from account. And of course, we have a parameter here of our price feed address. So we're going to have to add some type of parameter here. For now, let's just hard code it from our config. And we'll go into our config and we'll start our networks flag. We're going to be working, like I said, on the mainnet fork for this quick and dirty here. We'll call eth_usd price feed. We'll grab the eth_usd price feed from mainnet, since we're going to be doing a mainnet fork here. Pop that in here. Now we can just say from config networks network.show active eth_usd price feed. Of course, we're going to need to import network here. And now we can do our kind of quick and dirty test. We can do lottery dot get entrance fee. Am I spelling that right? Get entrance fee. Yes. Assert lottery.get entrance fee should be greater than, let's just go down one, 18. Or if we wanted to make sure we're actually doing this right, we'll do from web3 import web3. We'll do web3.toWay 0.019 comma ether. Should be greater than, and then we'll even do 0.018 just to make sure, and it should be less than 0.022. Now these numbers are of course going to be a little bit different for you, and if you want you can go ahead and skip this part so that you don't have to do the math, but it is kind of nice to do a quick sanity check saying, okay, like based off what things are right now, what would this price end up to be? Now in our last section we made a mainnet fork dev network. I'm going to just go ahead and customize our mainnet fork the way that we showed you guys how to do mainnet fork dev. This way you can use accounts and we can be a little bit more robust here. To do this, we're first going to have to delete Brownie's internal built-in mainnet fork. So we'll do Brownie networks delete mainnet fork. Mainnet fork has been deleted. And now let's go ahead and add our own mainnet fork using Alchemy as our Ethereum connection. So you'll want to create a new app. I've already created one here called Smart Contract Lottery. We'll view the key, and this is the HTTP endpoint that we'll use. So to do this, we'll do Brownie networks add. This will be a development chain. We'll call this mainnet fork. It'll be a ganache CLI. The host is going to be our local host, so 127.0.0.1. And the fork is going to be equal to our Alchemy HTTP here. We'll do accounts equal 10. That way we can use the accounts. We'll do the mnemonic equals Brownie. And port is going to be 8545. And great, mainnet fork has been added. Now that we have this here, we can go ahead and run our test. Brownie test -- network mainnet fork. Whoops, looks like we got a little compile error on our math here. Whoops, it looks like we're divided by price when we need to be divided by adjusted price. And we forgot the parentheses on latest round data. Let's try this again. And I put an extra comment in here. Let's try this one more time. Lovely. And it looks like we're forking correctly. And awesome. It looks like our test indeed passes here. Of course, we know that we're going to want to change this because this isn't a great way to actually test our contracts here, but it can be a nice sanity check. And we know we're going to have to refactor this as well for mocks and for accounts, but we'll get to that in a little bit. Awesome. Sanity check complete. Let's get back to our contract here. So we are getting the cost to enter correctly. Perfect. We're getting this entrance fee. What that means we can do in our enter function, we can do require message.value. It's got to be greater than or equal to our get entrance fee function. And if it's not, we'll give them an error of not enough ETH. We have a way for them to enter, and we have a way to get the entrance fee. But we want to make sure that we're not ending the lottery before the lottery even starts, right? Or we're not entering a lottery when a lottery hasn't even begun. So we're going to want a way to iterate through the different phases of this lottery. And we can do that with what's called an enum or an enum. According to the Solidity documentation, enums are another way to create user-defined types in Solidity. We saw an earlier version of doing this with a struct. Enums are a little bit different in that they're explicitly convertible to and from all integer types. So what does that actually mean? Well, we can have an enum like this, action choices, go left, go right, go straight, and sit still. They're just more readable ways to say go left is going to be represented as state 0, go right is going to be state 1, go straight, state 2, sit still, state 3. So for our lottery contract, we're going to want to create this new type that represents the lottery state. So to do this, we'll do enum lottery state open, closed, and calculating winner. This means that we have a new type called lottery state with 3 positions, open, closed, and calculating winner. These different states are actually represented by numbers. So open is actually a 0, closed is actually a 1, and calculating winner is actually a 2. Now that we have this new type, we can create a variable of type lottery state. So we'll say lottery state, public, lottery state. And right when we initialize our contract here, we're going to want to set our lottery state to being closed. So in our constructor, we'll do lottery state equals lottery state dot closed. Now, since these are represented by numbers as well, we could also just do lottery state equals 1, because 1 stands for closed. However, it's much more readable to do lottery state dot closed. Now that we have a lottery state, in our enter function, we can require that the lottery state is going to be equal to lottery state dot open. So we can only enter if somebody's started this lottery. And that's exactly what we're going to do in our start lottery function. We're going to do a require in here that the lottery state is going to be equal to lottery state dot closed. And we can even add a failure function in here saying can't start a new lottery yet. And when we do start this lottery, we'll say lottery state equals lottery state dot open. Now, when somebody starts the lottery, they'll be able to enter. Of course, this start lottery bit here needs to be called only by our admin. So this is where our only owner modifier is once again going to come into place. We could write our own only owner modifier, or we can once again use OpenZeppelin's access control and OpenZeppelin's ownable function instead, which is what I'm going to use here. So we're going to go ahead and grab this, copy this, paste it in, import at OpenZeppelin/contracts/access/ownable. And of course, since we're doing this, we're going to have to add this dependency into our config. We're going to be using OpenZeppelin/open Zeppelin contracts at 3.4.0. We're going to remap at open Zeppelin equals this. Oops. And then we'll say our lottery is ownable. Perfect. Now we'll try to compile this. Awesome. Looks like Brownie grabbed everything correctly and we're good to go. Great. Now we can finally move into our end lottery function. This is where we're actually going to choose a random winner here. We only want the admin to be the one to actually end the lottery. So let's add the only owner modifier here. And let's talk a little bit about randomness, because this is what we're looking to do now. We're looking to get a random winner here. Now, as you know, the blockchain is a deterministic system, right? And this is super advantageous because it allows us to do all these smart contracts and have this system that can actually reach consensus very easily. Random numbers are much harder. If, let's say, you had a blockchain with a whole bunch of different nodes and each node responds and gives their own random value, well, each node is never going to be able to sync up and say, hey, we all agree on a random number. What you could do is you could base the random number on some other attributes in the system, but then it's not really random. It's actually going to be pseudo-random. So getting truly random numbers in a deterministic system is actually impossible. And if you know a lot about computer science, you actually know that even when you call like math.random in your JavaScript, what your computer is really doing is it's looking at some place in memory, grabbing some value and saying, hey, this is probably random enough. Here, go ahead and use this. Now in smart contracts, especially when working with any type of financial application such as a lottery, having an exploitable randomness function means that your lottery is at risk of being hacked or destroyed. And this isn't even a fairy tale. At the time of recording, about 2 weeks ago, I did a rundown on an exploit where a protocol used insecure randomness and got hacked for $700,000. So I am going to show you this insecure way first. And the reason that I'm going to show you is that it is a quick and dirty way to get a pseudo random number, but please do not use this in any production use cases. I'm going to show you a method that's often used to teach people how to get random numbers, and then we're going to explain why it's so vulnerable and not a good method of randomness. And what some insecure protocols will do is they'll use a globally available variable and hash it. So in your smart contracts, there's actually a number of globally available variables. One of those, as we saw above, is going to be message.value, right? It's going to be the value that's sent with a transaction. Another globally available variable is going to be message.sender. You can actually see a whole list of these different globally available variables in the Solidity documentation here. So since there are all these globally available variables, a lot of times someone will see something like block.difficulty, which returns the current block difficulty. Now, one of these globally available variables is going to be block difficulty or block.difficulty. It's the current block difficulty. Remember how I said that the time between different block generation is called the block time? Well, you can always keep that block time as is by changing the block difficulty over time. The harder the problem or the harder the proof of work algorithm, the longer it's going to take, or the more nodes you're going to need to solve that problem. There's this constantly recalculating metric called Ethereum difficulty or block difficulty, depending on the chain that you're working on, that constantly changes. So you might think this would be a great use of randomness, right? Because it's a somewhat hard to predict number. So what a lot of people do is they think that, hey, those sound pretty random. Let's use them as a unit of randomness. And what you'll see is, like something like uint, Kachak 256, which is, again, this hashing algorithm. And they'll do something like abi.encode packed, nonce message.sender, block.difficulty, block.timestamp, mod, players.length. So I know there's a whole lot going into this line, and let's talk about it. So first, as we can see, is that we're casting or we're converting everything in here to being a uint256. The reason that we're doing this, of course, is because we're going to want to pick a random winner based off of an index, right? We're going to want to pick somebody some random winner in our players array or our players list. So we say, okay, whatever number that we're going to use, that's going to be the index of the winner that we're going to randomly pick. Then they use Kachek 256, which is again our hashing algorithm. So they hash a whole bunch of variables together, and they do this ABI.encode pact. ABI is another keyword for some low-level work. They'll add maybe a nonce in, they'll add the message.sender, block.difficulty, and block.timestamp. Basically, what they're trying to do here is take a bunch of seemingly random numbers, mash them all together in a hashing function, and then say, yeah, this is pretty random. But the issue here is that the hashing function itself isn't random. The hashing function is always going to be exactly the same. Kachek 256 is always going to hash everything exactly the same way. So we're not actually making it more random by hashing it. All these numbers inside are the pieces that actually determine how random it is. So if the block.difficulty is random, then this will be a random method. If the block.difficulty isn't random, then this won't be a random method. And the block.difficulty is not random. Difficulty can actually be manipulated by the miners. And timestamp is predictable. Nonce is predictable, aka transaction number, because in this regard, they're using the nonce as some transaction number. And message.sender is predictable. When using a random number in this way, the hashing algorithm is always going to be the same. uint 256 is always going to be the same. We have a predictable number, a predictable address, a predictable timestamp, and then a manipulatable value. So all this is really doing is giving the miners the ability to win the lottery or win whatever lottery that you're working on. So this isn't going to be an effective way to get a random number. This is an unacceptable way to get a random number in our applications. Yes, we do have this only owner modifier here, which means that we are the ones who are going to choose when to call this. So it is still centralized in that regard. But let's just teach you the best practices for working with random numbers right from the get-go so you don't run into any issues. I'll explain what this part is doing in a little bit. In order to get a true random number, we are going to have to look outside the blockchain. The blockchain itself, like I said, is a deterministic system. So we need a number outside the blockchain. But what we can't do is we can't use just an API that gives a random number, right? If that API becomes corrupted, if they're malicious, if they go down, if something happens, etc. What we need is a provable way to get a random number. And Chainlink VRF is actually that solution. Chainlink VRF stands for Chainlink Verifiably Randomness Function. And it's a way to get a provably random number into your smart contract. It has an on-chain contract that checks the response of a Chainlink node to make sure the number is truly random. Using some cryptography magic, it's able to check a number of the parameters that the Chainlink VRF started and ended with to make sure that it's truly random. It's already used for protocols like Avagochi, Ether cards, Pool Together, and a whole bunch of other protocols as well, because it is a secure, reliable, truly provable way to get a random number, which is incredibly powerful in a decentralized system. So that's how we're actually going to get our random number here. So let's work on getting that. What we can do is we can go ahead and head right over to the Chainlink documentation to actually learn how to work with one of these. Let's go over to the Chainlink documentation just to make sure that we get it right. So if we go to the get a random number here, we have all the documentation you could ever want. So if you ever get lost or confused, you can always come right back here to work with it. What we're going to do is we're going to deploy their simple version in Remix version of working with the Chainlink VRF. And we're going to walk through a minimalistic contract to see how it actually works in a contract. So once again, we're hit this Remix button, Remix pops up, and we immediately get this random number consumer.sol in our files that we can check out. So awesome. So here is our files right here. We can see that this is actually using a different chain than what we've been using. We've been mostly working with Rinkeby, but for this demo, it's actually on Kovan. So we can do some work with Kovan here. And remember, if you do want to stay with Rinkeby, you can always go to this contract addresses section of the VRF and grab these addresses to use. So what's going on in this contract? How do we actually use this? Well, as you can see, the first thing that happens is we're importing some code from the Chainlink package. And our contract is inheriting the abilities of this VRF consumer-based contract. So we're going to see what functions we're actually going to use that are inherited from this contract. And the first thing that we notice is we can see that our constructor in here does some weird stuff. It looks like it almost has two constructors. So what's actually going on here? Well, let's look at this vrf consumerbase.sol contract in the Chainlink GitHub. So we can come to the Chainlink GitHub here. We'll go to EVM contracts, or depending on when you're watching this, it's migrating to contracts at some point. We'll go to EVM contracts. We'll go to SRC. So once we're using v0.6, we'll go there. And we'll look at this vrf consumerbase.sol. As we can see, this vrf consumer base that we're importing has its own constructor, and it takes an address for the vrf coordinator. This is the on-chain contract that actually checks to make sure our numbers are random, and the address of the Chainlink token, which we'll talk about ERC20s in a little bit. What we're doing is we're also inheriting the constructor into our contract. So this is our constructor for our random number consumer, but we can also use the constructor of the vrf consumer base. And this is actually how we go ahead and do that. We grab the constructor of the vrf consumer base and plop it in here. Now it's taking two addresses. It's taking the vrf coordinator and the link token. Like I said, the vrf coordinator is a contract that's been deployed on chain that's going to verify that the return of the Chainlink node is truly random. And we're going to use the link token as a payment to the Chainlink node for its services. And then we also have a key hash and a fee defined inside of this constructor as well. The key hash uniquely identifies the Chainlink node that we're going to use, and then the fee is how much link we're actually going to pay to the Chainlink node for delivering us this random number. Now let's talk about a couple things here. In Ethereum, whenever you make a transaction, you have to pay some ETH gas, right? Or transaction gas. This is to pay the smart contract platform a little bit of ETH for performing our transaction. With a smart contract that operates with an oracle, we have to pay some link gas or oracle gas. This is to pay the oracles a fee for their services for providing data or doing some type of external computation for our smart contract. The question that might then follow up is, oh, okay, well, how come I didn't have to pay when we did this price feeds thing? Well, for price feeds, somebody had actually already paid for the data to be returned. And if we go to data.chain.link and we scroll down, we can actually see a list of sponsors here that are paying to get this data delivered. So they're already paying the oracle gas to bring this data on chain for us. Since no other protocol is getting a random number for us, we're actually going to have to pay the oracle gas here. Now, in this contract, we have a function called getRandomNumber, which is going to return a bytes32. And what it's going to do, it's going to call this request randomness function, which is inherited from this vrf consumer base. If we look in here, we look for request randomness, we can see there's a function right here called request randomness. This function is going to send our oracle fee or the link token, and it's going to call this specific to the link token function called transfer and call. This function is going to call a Chainlink node. Now I'm not going to go into exactly how it's doing that right now, but we will talk about it in a little bit. So we call this request randomness function, and we send the key hash and the fee. Remember, the key hash uniquely identifies the Chainlink node, and the fee is going to be how much oracle gas we're going to pay. If you ever get lost on how much to pay or what the contract addresses are, you can always head over to this vrf contract section and see where the most recently deployed VRFs are, how much the fee is, etc. Now here's where it gets a little bit interesting. Getting a random number actually follows what's called the request and receive style of working with data. Let's go ahead and just try this out, and I'll explain what this means once we see it. Now we're going to save the answer to this random result variable here, and let's just go ahead and try this and see what happens. So we're going to switch to our injected Web3. And since we're now swapping to a new test network, this means that we have to get testnet ETH and testnet link again. We can always look for the link token contracts page to find the most up-to-date faucets. So we'll scroll down, we'll find Coven. Looks like this is the testnet link faucet and the testnet ETH faucet. So here's our Coven faucet. We'll just want to switch from Rinkeby to Coven. We'll grab our address, paste it in, send me a 100 test link. Here's our transaction. We can see we're transferring some ERC20. We'll take this contract address, we'll add it to our MetaMask by copying the address, scrolling down to add token, pasting it in here. I already have the address in here, so I'm just going to go ahead and hit cancel for now. And we'll also want some testnet Coven Ethereum, which looks like this faucet has it. So we'll paste the address in here. I'm not a robot. And we'll do send me 0.1 test ETH. And perfect. Now that we have some testnet Ethereum and some testnet Link, we can proceed. We're going to make sure we're on the Coven test network, and we're going to deploy our random number consumer gist here. Let's go ahead and hit deploy. MetaMask pops up. We're going to go ahead and confirm. I didn't explain this fulfill randomness function intentionally. You'll see why in a second. And great, a random number consumer comes up. Let's check what our random result is right now. It's obviously 0 because we haven't got a random number. So I'm going to do something intentionally wrong because there's a good chance that you'll run into this at some point. If I hit get random number right now, we see this error gas estimation failed. We have plenty of ETH. Why would this fail? The reason that it's failing is because the contract doesn't have any Oracle gas. So we got that gas estimation failed because we need to fund this contract address with some link to actually get a random number. So we're going to hit this copy button, and this is going to copy the address. And we're going to come into our MetaMask here, and we're going to send this address. We're going to paste it there, swap to link, and we'll send it one link. This is probably overkill because, as you saw, the fee is only 0.1, but we're just going to be overkill for now. And great, now that this contract has some testnet link, now we can call this get random number button because we can actually pay the Chainlink node to actually return our random number. So we're going to go ahead and do confirm. And this is fantastic. So we're paying a little bit of transaction gas to make this transaction, to make this request. And then we're paying a little bit of Oracle gas to make this transaction. Now, so the transaction confirmed, but if I hit random result now, it's still going to be 0. So why is that? What's going on? Well, getting a random number like this actually follows what's known as the request and receive cycle of getting data. You can read more about it here in this basic request model in the documentation. So in one transaction, we actually request some data, or in this case, a random number. And then in a second transaction, the Chainlink node itself will make a function call and return the data back to the smart contract. In this case, the function that we're calling is fulfill randomness. It calls this fulfill randomness with bytes32 request ID, which is going to be the request number of when we called this, and it's going to return with this random number called randomness. So after we wait a little bit, if we hit random result now, we can see indeed our random number is in here. And again, the reason that it's in here is because we actually had 2 transactions occur. One paid by us when we called get random number, and one paid by the Chainlink node when it called fulfill randomness. Now, I lied to you a little bit. Technically, that VRF coordinator contract calls this function, and then the Chainlink node calls the VRF coordinator function, but for simplicity's sake, you can kind of just think of it as the Chainlink node itself is calling this fulfill randomness function. So now that we know how to do this in Remix, let's go ahead and add this to our Brownie project. So actually, before we even do that, we need to require. So before we even get a random number, let's change the state of our lottery. So now we'll do lottery state equals lottery state dot calculating winner. And while this is happening, no other functions can be called, right? This will lock out. Nobody can start a lottery and nobody can enter a lottery while we're calculating the winner. Awesome. So now that we know a little bit more about random numbers and everything that we're doing here, let's go ahead and try implementing this now. So in our Chainlink smart contract docs, of course, we're going to scroll down. We're going to go to our get a random number bit here. We can copy and paste all this code as well into our smart contracts. So the first thing that we're going to need to do, of course, is import the VRF consumer base code. Let's move back over, scroll to the top, and we'll just paste this in at chainlink/contracts/src v0.6 VRF consumer base, and we'll inherit this into our lottery contract. So we'll say the lottery is VRF consumer base, and it's ownable. Let's take a look at this VRF consumer base in the Chainlink GitHub here. If we scroll down to the constructor of our VRF consumer base, we can see it takes these 2 parameters, the the address of the VRF coordinator, and the address of the chainlink token. We can use a constructor of a contract inherited in our contract inside our constructor. So what we'll want to do is we'll want to come down to our constructor, and right after this public keyword, we can add any additional constructors from inherited smart contracts. So we'll say constructor, and this is our normal constructor, and then we'll put VRF consumer base. And we'll add the VRF consumer base addresses in here. We know that it's going to be a VRF coordinator address and a link token address. Similar to the price feed, these two addresses are going to change based on the blockchain that we're on. So it'll probably make sense for us to parameterize them the same way we parameterize the price feed address. So in our top level constructor parameters, we'll add an address for the VRF coordinator, and we'll pass this to the constructor of our VRF consumer base. Then we'll also grab an address for the link token. So we'll do address, link, and we'll pass this to the VRF consumer base constructor as well. Great. What else do we need to make this work? Well, back in the documentation, we can see we need a fee and a key hash. The fee is associated with the link token needed to pay for this request. So we'll make a public variable, uint256 public fee. Since this might change blockchain to blockchain, we'll have this as an input parameter as well. So we'll do uint256 underscore fee, and in our constructor, we'll do fee equals underscore fee. We'll set our global variable to fee. And I need a comma here and no semicolon here. What else do we need? Well, we need a key hash. The key hash is a way to uniquely identify the Chainlink VRF node. So we'll create another one. We'll do bytes32 public key hash. We'll add this as a parameter in here. Bytes32 key hash. And then we'll say key hash equals underscore key hash. Perfect. Our contract is coming along great here. Now that we have the main pieces that we need, how do we then request this random number? Well, if we scroll down in the documentation, we can see we have this request randomness function that we need to call. If we scroll back to our VRF consumer base contract, this request randomness function is a built-in function from the VRF consumer base. So our contract can natively call this request randomness function right in our contract. And you can see it takes a key hash and a fee as its parameters. So right in our end lottery function, we can add this function. And we can see this also returns a bytes32 called request ID. This return syntax is pretty powerful. You can actually identify the name of the variable you want to return right in your function declaration. So by saying bytes32 request ID, we're saying we're going to return a bytes32 variable named request ID. So right in our function here, we can do request randomness, because again, that's this function that we're importing, passing it the key hash and the fee. This will return a bytes32 called request ID. So this is actually doing this and having our function declaration tell us that there's going to be a variable named request ID is going to be exactly the same as if we did bytes32 request ID equals request randomness. Now, this function call follows, again, what we've talked about as the request and receive mentality, the request and receive architecture. This means that in this first transaction, we're going to request the data from the Chainlink Oracle. In a second callback transaction, the Chainlink node is going to return the data to this contract into another function called fulfill randomness. So again, if we look back in our VRF consumer base, we can see it has this function raw fulfill randomness. We can read some of the comments in here saying raw fulfill randomness is called by a VRF coordinator when it receives a valid VRF proof. Raw fulfill randomness will then call fulfill randomness. So there's a little bit of contract tag going on, but it's going to eventually call this fulfill randomness function. which is going to be what we define in here. And that's how our contract is going to know what to do once it gets the random number back. So in our first transaction, we're going to end the lottery, request a random number, and then in a second transaction later on, once the Chainlink node has created a provably random number, it's going to call a second transaction itself based off of what we define. We just have to call it fulfill randomness. And as you can see, it takes a byte 32 request ID and a random number. So in here, we'll do fulfill randomness, takes a byte 32 request ID, and then a uint 256 randomness. We don't want anyone else to be able to call this function. We only want our Chainlink node to call this function so we can return a truly random number. So we're going to make this an internal function. It's internal because actually the Chainlink node is calling the VRF coordinator, and then the VRF coordinator is calling our fulfill randomness. So we'll make this internal so that only the VRF coordinator can be the one to call and return this function. And then we're going to give it a keyword of override. This override keyword means that we're overriding the original declaration of the fulfill randomness function. Our VRF consumer base has a function fulfill randomness defined, but it doesn't have any parameters or anything about this function actually laid out. This function is meant to be overridden by us, and that's exactly what we're doing right here. So in this fulfill randomness function, let's go ahead and define what's going to happen once we get this random number back. So before we can process this random number, let's just check to make sure we're even in the right state. So we'll do require. Our lottery state is going to be equal to lottery state dot calculating winner. And if we're not in that state, we'll just say you aren't there yet. My auto format is on for this one, so it's jumping in. Then let's just do another check to make sure we actually get a response. So we'll do require underscore randomness is greater than 0. And if it's not, we'll just say random not found. Now we need to pick a random winner. Well, we need to pick a random winner specifically out of our list of players, our list of payable public players. So our players array is just a list of players. So it's like player 2, player 3, player 4, and they're each at a different index. What we can do then to pick a random winner is to do what's called a modulo function. In fact, let's even open Remix to do an example of this. Remix, let's pop open a new contract. We'll call it mod.sol. We'll do pragma solidity caret 0.6.6. We'll do contract mod. And in here, we'll do a constructor, blank constructor, and we'll get a global variable, uint 256, number, and we'll set it equal to 5. And we'll go down to 0.6.6. We'll save, compile, and let's even just get rid of the constructor. Let's now create a function called doMod. We'll take a uint 256 mod value, make this a public function. Public view returns uint 256, and we'll just return 5 modulo mod value. Now let's go to JavaScript VM. We'll deploy this. We'll go in here. So our number is right now 5, and let's learn about how the modulo works. If we have this doMod function, what we're doing is the module divides by the number and returns the remainder. For example, if we did 5 mod 5, what do you think we're going to get? So we're going to do 5 divided by 5 and then return the remainder. Well, 5 divided by 5 is 1, and there's no remainder. There's no decimal there. So 5 mod 5 should be what? 0, exactly. Well, what's 5 mod 4 then? Well, 4 can go into 5 evenly once, but there's one number left over. So 5 mod 4 is going to be 1. 5 mod 3 is going to be 2. 5 mod 1 is going to be 0, right? Since 1 goes with everything. This is how the mod function works, and it's this little percent here. We can use that mod function in our fulfill randomness with the length of our players. So we can say uint 256 index of winner is going to be equal to the random number that we got modded by the players dot length. So let's say, for example, we had 7 players sign up and our random number was 22. Well, we want to get one of these random 7 players. So we would do 22 mod 7. 7 divides evenly into 22 3 times with 1 left over. 7 times 3 equals 21. Difference between 21 and 22 is 1. 7 times 4 is 28. So we know, this is how we know we've reached our upper limit. So this is how we can get a random number based off of the index. Now that we have this index, what we can do is we can say the winner equals players of the index of winner. And just to keep track, let's make a new variable called recent winner at the top. We'll do address public recent winner. We'll grab this recent winner. Instead of winner, we'll say recent winner equals players in this index of winner here. Now that we've got a winner, well, we want to pay them all of the money gathered from our enters here. So what we can do is we'll do this recent winner dot transfer the entire balance of this address. So we'll say address of this dot balance, and perfect. We'll transfer them everything that we have. Then of course, we're going to want to reset the lottery so that we can start from scratch. We can start blank again. So we'll do players equals new address payable array of size 0. So we're just resetting players to just be a brand new array. Then we're going to change our lottery state to being lottery state.closed because the lottery is now complete. And I often also like to keep track of the most recent random number. So at the top, I'll do a uint 256 public randomness variable. And in our fulfill randomness, I'll say randomness now equals underscore randomness. And perfect, we now have a contract here. Of course, we haven't actually tried it out, but we're assuming that it works great. So you know what this means. It's time to go into testing mode, testing and development mode. But let's even just try to do a brownie compile first. Looks like we have an issue here. Send and transfer are only available for objects of type address payable, not address. Oops. Looks like we made our recent winner just an address, but it needs to be an address payable. So let's try brownie compile again. And beautiful, we at least know it's compiling, so that's a great sign. Let's now move into our testing and development phase. As you are starting to figure out, we can ignore these file import callback not supported bugs in VS Code for now. I'm sure the Solidity linter will get better as time progresses. But great, so now let's go ahead and move into actually testing and working with everything here. So let's go ahead into our scripts, and we'll make a little deploy script first. Let's do a new file. We'll call it deploy lottery.py, and let's go ahead and deploy our lottery. So same as always, we'll do def main. We'll come up with a new function called deploy lottery, and then we'll do def deploy lottery, and then we'll just have a pass for now. And if we run this, brownie runs scripts, deploy lottery.py. Our default network is not defined, which means the default is going to be development. And we can even be verbose here, development, write that in our brownie config. Run this, a ganache will get spun up, and nothing will happen because our deploy lottery function doesn't do anything right now. Awesome. The first thing we need always to deploy a contract is we need an account. So we'll do account equals, and we've been using this get account function for some time that we've been adding in a helpful script section so that it can pull from a real testnet or from a local development environment if we like. So to do this, of course, let's create our new helpful scripts.py. We'll create our init__init__.py so that Python recognizes it as a package. And in here, we'll create a new function, def get account. For now, we'll just have it pass. We'll copy this into our deploy lottery. We'll do from scripts.helpful scripts import get account. Now this is what our get account looked like in our last project. Along with that, we had these forked local environments. We also had from Brownie import accounts and network and config to make this look really nice, right? Let's flesh this out just a little bit more so it's even more robust. Right now, as we know, we have a way to use Brownie's Ganache accounts, and we have a way to use our environment variables. However, there was a third method that we learned that isn't identified here, accounts.load, and this is with our ID. If you still have your account and you still have all your Brownie set up, if we do Brownie accounts list, you'll see we have a couple accounts here. We want our get account to be even more liberal so that if we wanted to use one of these as well, we could. So let's modify our get account script here a little bit. Let's first get rid of this else and rid of this indent. What this will do is this will be our default. If nothing that we define prior to this is defined, we'll just default to grab right from our config, which, since we are doing that, let's create our .env. We'll paste our different variables in here, our private key, Web3 Infura, and Etherscan token. And in our Brownie config, of course, we'll do wallets, from key, private key. And now let's flesh this out a little bit. Let's add an index and an ID. Index equals none, and ID equals none. This way, if we pass an index to our getAccount function, we'll just use an index from this accounts variable. If we pass an ID, we'll have trying to do this accounts.load here. So now let's change this up a little bit. We'll say if an index was passed, we'll just return accounts on that index. Otherwise, if we're doing a local blockchain, we'll just return accounts 0. But if there's an ID, we'll return accounts.load ID. Whoops, we need to actually move this up a little bit so that it's before our local blockchain checking. So now in our deploy lottery, we could do something like get account ID equals free code camp. Whoops, and this is actually free code account. Free code camp account. Let's try one more time. It's going to ask for our password here. Now we have a much more liberal get account function. So now that we have account, we can actually deploy our lottery. So we'll say lottery equals lottery.deploy. And this is where we're going to import from Brownie, import our contract lottery. And we're going to have to add in all of these different variables. So if we go back over to our lottery contract, we need to give it a price feed address, a VRF coordinator, a chain link token, a fee, and a key hash. Now, the way we did that in FundMe is that we did it in a way where we checked to see if we were on a local chain or not. If we weren't on a local chain, then we would just pull our addresses directly from our config. If we weren't on a local chain, though, we'd deploy some mocks and use the address of those mocks. We're going to want to do the same thing here, but let's make our lives a little bit easier. We can take this whole process and put it into its own function. So let's make this a little bit easier mentally. The first thing that we're going to need is this price feed address. If we're on a real testnet, of course, we would just go into our Brownie config and add the address, which we will do. We'll add our RINC-B network here in a little bit. But for now, don't worry about that. But if we're not on a RINC-B chain, what we're going to need to do is deploy our mock. We're going to wrap all of this mocking and checking into a single function called getContract. And we're going to add this function in our helpful scripts. So let's create this function called getContract. So do def getContract. Pass. And let's talk a little bit about what we want this function to do. Let's add 1, 2, 3 double quotes here and 3 double quotes here to start what's called a docstring. This will define everything about this contract. So we're just going to say this function will grab the contract addresses from the Brownie config if defined. Otherwise, it will deploy a mock version of that contract and return that mock contract. For the arguments of this chain, we're going to take a contract name. This is going to be a string, and it'll return a contract. Or in particular, it's going to return a brownie.network.contract.project contract, the most recently deployed version of this contract. So for example, if we have a mock v3 aggregator contract, it'll do the most recently deployed version of that with this -1 syntax. Now this getContract function, if this is a little confusing to you, again, we're going to go over this chain link mix in a little bit. And inside of this, it has a more robust description of what's going on in this getContract bit. So you can check that out if you want to learn more. But let's go ahead and actually define this. So we obviously want a contract name as an input parameter. So let's go ahead and add contract name in here. Meaning that this getContract function will get something like FUSD price feed, right? That's going to be the same as what's defined in our Brownie config. And from this name, we're going to get the type of contract that it is. Contract type. And to do that, we're going to have to create some mapping that'll map the contract names to their type. So right above, we're going to do contract to mock. And we're going to create a mapping in here, which will map everything out. So an FUSD price feed is going to be of type mock v3 aggregator. So we're going to have to import mock v3 aggregator from Brownie. So now we're saying anytime you see FUSD price feed, you know that that's going to be a mock v3 aggregator if we need to deploy a mock. So we'll say contract type is going to equal contract to mock of the contract name. Now we need to check, okay, do we actually even need to deploy a mock? So sure, let's check if we're on a local blockchain. So we'll say if network.showActive is in our local blockchain environments. And we'll skip the forked local environments because, again, we don't need to deploy a mock price feed address on a forked local environment. We'll say if network.showActive is in the local blockchain environments. Then we'll check to see if one of these contracts has already been deployed. We'll say if the length of contract type is less than or equal to 0, then we're going to go ahead and deploy mocks. So this is equivalent to doing something like mock v3 aggregator.length. We're checking how many mock v3 aggregators have actually been deployed. If none have been deployed, we're going to go ahead and deploy them. So we're going to have to create this deploy mocks function. So we'll do def deploy mocks. And this is going to be the same as what we did in our Brownie fundme, right? It's going to be the exact same. So we'll say account equals get account. I'm not going to put the prints in here, but you absolutely can. we'll say mock price feed equals mock v3 aggregator deploy. We'll need to give this some decimals and an initial value. So right above, we'll do decimals equals 8, initial value equals 2000, 2000, 1, 2, 3, 4, 5, 6, 7, 8. And in our deploy mocks, we'll say decimals equals decimals, initial value equals initial value. To deploy decimals and initial value, of course, this is going to be from account. And for now, that's it. We'll just say print deployed. All right, great. So now we have a way to actually deploy the mock price feed here. So let's go back up to our get contract function. So we have a way to deploy the mock if one already isn't deployed. Now what we're going to want to do is we want to get that contract, right? We're going to want to get that mock. So we'll say contract equals contract type -1, right? So this is going to be equal to doing mock v3 aggregator -1. This is saying, hey, let's grab the most recent deployment of the mock v3 aggregator, which is exactly what we want. Perfect. So this will work perfectly for our development context. However, we're not always going to just want to deploy to a development network. We're also going to want to deploy to testnets. So then we'll say else, and this is where we'll just grab that contract from the Brownie config. For example, ethusd price feed. So we'll say contract address equals config networks network.show active, and that contract name. For example, again, if it's ethusd price feed, it'll be ethusd price feed here. And the way we're setting it up, it's got to be the same as what's in our contract to mock dictionary here. So up here, the way that we did it was we actually got the contract because we had its contract type based off of Brownie. For here, we're going to have to interact with the contract, getting those two pieces that we always need, which are going to be the address. We actually have the ABI from our mock v3 aggregator type right here, and we just got the address. So we can create this new contract type by saying contract equals contract dot from ABI, and this contract package can be imported right from Brownie, and it has this function from ABI that allows us to get a contract from its ABI and its address. So we'll just give it a name. We can say contract type dot underscore name. We can do the contract address, and then the contract type dot ABI. So these mock v3 aggregators and all these contracts have a .ABI attribute that returns the ABI. They also have a underscore name, which returns their name. So this is perfect. This is how we'll get the contract otherwise. And then at the end of all this, we'll just do return contract. Awesome. So this is an incredibly powerful function for us to get a contract based off of if it's already deployed as a mock or it's a real true contract. I know there's kind of a lot here, but definitely check the GitHub repository if you're a little bit confused on what's going on with this function. And let's also just deploy this to make our linter happy. Why not? Yay, VS Code's happy now. But now that we have this function, let's go back to our deploy lottery. Now we can do a comma, get account, and now we have a get account function. So let's go through this again. This lottery.deploy get account is going to get an ethusd price feed. If we don't have a mock deployed, it's going to deploy a mock price feed for us, and we're going to return that mock price feed. However, if we're on a test net, if we're on a real network, we're going to grab its actual address and return a mock contract of it. Our mock contract here has all the same functions of a regular contract, so we can just use it as the same. This way, we don't have to adjust this function for whether or not we're deploying to a test net or to an actual address. The only additional piece we should put in here, just for clarity, is we should add